Okay, so this will be a continuation of my complex analysis playlist, and in this video I'll be talking more about nonlinear Cartesian mappings. Remember in the previous one I talked about we had a function f of z is equal to z squared, and I did an example of what happens when we try to map from x and y over to the UV plane. We had the function r z squared, and we were given a line and here as our pre-image, and we wanted to know what the image of that looked like in the complex plane. So here we're going to be continuing that. And hopefully after this example you'll have a better idea of what's going on. So if you watch that video and this video, you'll have a good understanding of Cartesian mappings. Of course, doing a couple of them is really good practice. And you could do thousands of examples of different, you can come up with any complex function you can think of. But I think some of the most interesting ones to start off studying would be z squared and probably z to the 1 over n. However, of course, you can do z cubed, z to the 4th. However, those get a little bit messy to do, so those are probably not good practice exercises, but definitely z squared is a good one to understand. So again, here, I have the notation, our pre-image is our function u, and then our output's v, and then our function maps u to v, and then our image is f inverse of v is equal to u. Now, the purpose of this was, if you're not familiar with that notation, it's definitely good to understand that notation. Now, this is not typically the notation that's used with complex analysis, but nonetheless, this is important to get this down. So now that that's out of the way, I'm going to go ahead and actually start the problem. And you'll see that this problem really isn't all that tricky. So again, it's just really just a matter of practice. So basically, so we have our function a is we have x and y, and our line is x is equal to 2. I already made a mistake. I wrote 3. We'll start with x equal to 2. So what do we do here? Well, we start off with f of z is equal to z squared plus z. Now remember, we're dealing with Cartesian coordinates. And remember my golden rule of complex analysis. Whenever you see z, you can always write that as x plus iy. So we're going to go ahead and now write it that way. So f of x plus iy is going to be equal to x plus iy squared plus x plus iy. And so remember that this can simplify. This here simplifies to x squared minus y squared plus 2xiy, and over here we're just left with x plus iy. Now, so this is our f of x plus iy, and remember this is the part where we have to break the function apart into its real and imaginary components. And remember, we call the real part u and the imaginary part v. So x squared minus y squared, that's of course, that's real. So we have x squared minus y squared. And of course we also have x, because x is not multiplying I. Now for our v, we're going to have 2xy plus y. These are our functions here. Now of course this is a little bit more complicated than in the previous case, because before I only had 2x squared minus y squared plus 2xy. I didn't have an extra term adding that. But it doesn't really make much of a difference. So anyways, so remember what we did here. Or we can do it in a few ways. We can actually start by plugging in 2 for the u, or 2 for all the x's in the real part of the function. But I prefer to do it actually a different way. I actually start off with the v first. So, but you can do it either way. So let's just plug in our 2. So our v is going to be equal to, I'm not going to write that, I'm going to write it like this. So we have 2 times y plus y. So we have 4y plus y, which is just 5y. So our v is equal to 5y. And remember now we're trying to solve for y here. So we're going to have y is equal to v over 5. Now remember, what we're trying to do here, we're just simply trying to figure out what this function looks like when we map it over to the UV plane. So we have to have some way of relating x and y to the u and the v that it's going to go to. And this is really just all I'm doing here, that this is just a process that you follow in order to get from here to here. So y is equal to v over 5. So now I'm going to kind of just work over here a little bit. So now we're going to plug this into our u. So we're going to have u is equal to, and also in addition to that, we can actually now plug in our 2 for the u. So we can have 2 squared minus y squared. Remember our y is v over 5, so v over 5. And then we now add our x, which again is just 2. And so our u here is going to be 4, should be squared there, v squared over 25 plus 2. and so that can be simplified simply to 6 minus v squared over 25. And this is our u. And so our final, I guess I'll just call it, yeah, so essentially our image is going to look like this. We have uv such that u is equal to 6 minus v squared over 25. And that is our answer. I'm going to write that a little bit neater. It looks a little messy. So 6 minus v squared over 25. That is our answer. And that's essentially how you do all these mappings. But I'm not going to graph this right now because this is probably annoying to graph parabolas on the board here, especially with all this work here. But essentially, whenever you have lines in the xy plane, you're going to end up getting a parabola in the uv plane. And I mentioned that in the previous video. And you can, of course, do all these examples with just lines, and you'll see they map over to lines in the uv plane. And of course, it's a very simple case that we're doing just with lines. What if we had something more complicated? What if we had like parabolas here, or if we had, just other conics? We can get very crazy here, but for the purposes of just learning complex analysis, just get the gist of what's going on. Lines are just a definitely a good example, good examples to learn this material. So that's pretty much what the Cartesian maps are all about. So again, all we're going to do is we start with our function on the xy plane. We're given an x is equal to 2 or y is equal to something because we're only dealing with lines here. And we're trying to figure out what parabola that maps to in the uv plane. And our mapping here is z squared plus z. This is, we have to, of course, always keep in mind that we always work with this function here. And it can be simple like this, or it can be more complicated. I could, of course, put something like, z to the 1 over, 72. And of course, that'd be very weird, but that is, that's something that could, of course, happen. And so we have z squared plus z, and all we're really doing is replacing the z with x plus iy, getting our u and the v. Remember, u is real, v is imaginary. We're solving y or x. We're rearranging this equation here, and we're trying to solve for y or x. And when we do that, we're going to end up getting a v down here. And then we plug we plug this result back into our u, plug whatever's up here into our u, and from there we solve. That's how you do these types of problems. And you can, and also with polar coordinates, which I'm going to get into in my next video, polar coordinates follow the exact same idea. The only difference in polar form is that instead of having x plus iy, we're dealing with r e to the I theta. But the process you'll find is very, very similar. Of course, we'll have angles, and so it's going to be slightly different, but the general idea is the same. So anyways, I hope you guys enjoyed, and I'll see you guys in the next video.